In this video, we continue our explanation of how temperature affects the molar Gibbs energy of a substance by focusing on water. Okay, so the goal is to see how this graph that we have here for the variation of the molar Gibbs energy of the three phases of water, how that is affected by an increase in pressure. Okay, so we've drawn these lines before, and again, the only thing remarkable about them is that the slope of the line is going to be the minus molar entropy of each one of the phases. That means that a gas is more disordered than the liquid and the solid. The slopes will be greater for a gas, a little lower for a liquid, and a little lower for a solid. But the important thing here is that we're trying to understand now how this graph changes with pressure. Okay, so that will be our reference pressure, pressure 1, which we can take to be 1 bar, for example. Okay, and then the idea would be to modify this graph to see how it changes when you increase the pressure. Let's first label here the equilibrium points. That will be your vaporization or boiling point if the external pressure is identical to the vapor pressure of the liquid at this temperature, and this will be your fusion point or freezing point. All right. Now we increase the pressure, okay, and we're going to draw how these lines would look like for a pressure P2 greater than P1. The way that we do this is by taking any point in each one of the three lines, this one, and examining what happens to the molar Gibbs energy when you increase the pressure. Okay, so when you increase the pressure at constant temperature, that means that we're going to be moving in this axis vertically. Okay, if you increase the pressure, then the molar Gibbs energy should increase according to the molar volume. Okay, so this point is going to increase. Okay, and that increase is going to be commensurate with the molar volume. Okay, so you will do this for every single point in these lines, and then what you will get is that the lines turn out to be something like that. We can perhaps draw it with a greater offset here, yes, to make the representation a little better. We can draw it like that. All right, great. All right, so we can do exactly the same thing for the solid and the liquid. And again, the offsets are going to depend on the molar volume of the liquid and the solid. Now, the molar volumes of the liquid and the solid phases are much, much smaller than that for the gas. Okay, they're about 1,000 times smaller. So of course, we cannot draw a scale that is 1,000 times less than this in this graph, but you understand the approximation. Okay, now here's the important thing about water. It turns out that the molar volume of the liquid is smaller than the molar volume of the solid. Okay, this is the effect that makes ice expand or water expand when it freezes from the liquid. Okay? All right, and again, that's an anomaly that only happens for water and a few other substances, but none of the other substances are going to be of interest to us. All right, so then let's see what will happen for the lines of the liquid and the solid. Okay, for the liquid, or for the solid, this line is going to be offset by about 1,000 times less than these lines, but again, that's difficult to draw, so I'm going to draw them like about there. Hey. Yeah. And then for the liquid, the offset should also be positive and about 1,000 times smaller than that offset. But this offset that's the solid. That offset, solid, okay, is related to the molar volume. And notice that the molar volume of the liquid is a little bit smaller than the molar volume of the solid. Right, so when I draw this line right here, okay, that offset is going to be smaller than what I have for the solid. Okay. Okay, notice how the separation between those two lines is a little bit smaller than the separation between those two lines because that separation is again related to the molar volumes of the phases. All right, so with this graph we can then try to see where the new transition points are. Okay, notice that the new boiling point is going to be pushed upward in energy. Okay, so that is the new boiling point. That is the equilibrium between the liquid and gas lines. Okay, PV prime. And then what about the new freezing point? The new freezing point is actually going to be depressed. Okay, TF prime. Notice the difference between water and a regular substance. In a regular substance, the boiling point goes up with pressure. Okay, but for water that happens as well. But for water, the freezing point gets down or gets depressed with pressure. And for a regular substance, what we actually saw in a prior video is that it actually also increases. Okay, so that is the separation between water and not water for these graphs when you increase the pressure. Okay, that's an anomaly of water. The freezing point gets depressed when you increase the pressure. Now the question is, well, are there any applications in real life where we actually see this? Or the other way to think about this is, well, let's think about ice melting into liquid water or liquid freezing into ice when you actually are at high pressures. Where in the world does that take place? There's actually various places where that is pretty apparent. One of them is in glaciers. Okay, so when you think about a glacier, there's going to be a huge amount of ice that is resting on a bedrock. Okay, so that bedrock usually has some jagged edges from the rocks. Okay, that means that the pressure felt but the ice that is in direct contact with the rock is going to be huge, because you not only have atmospheric pressure, but you also have the weight of the height of the glacier, right? There's going to be thousands of tons of ice, again, resting on jagged edges of rocks, and the pressure is going to be very large there. Well, what that means is that because the pressure is so high, now water can survive as a liquid at temperatures well below 0 Celsius. Okay, so then what will happen is that what you're actually doing in that at the bottom of the glacier is by applying the pressure. If that ice is supposed to be at -10 Celsius, but now the near freezing point with the pressure goes down to -15, you can actually get liquid water at 10 Celsius, right? So the effect is that that ice that is resting on the rocks is actually going to melt into the liquid with pressure, okay, and then going to refreeze over, and that makes the glaciers advance downhill. Okay, so that's kind of the origin of glacier dynamics, the idea that glaciers can actually move. And again, that's because water, you can melt it, okay, with pressure in the bedrock, and then it refreezes, and it kind of continues downhill. Okay. Another place where this is actually observed, or we believe is observed, is in ice skating. I think about ice skating. You essentially are applying quite a bit of pressure on the ice, because the blades of the ice skates are very thin, right? So notice that pressure is equal to force over area. That area under which you're executing the pressure, or exerting the pressure, that area is actually very small, which means that the pressure is very high. So it is actually thought that every time that you go ice skating, okay, the pressure that you're applying on that ice is enough to actually melt it into the liquid instantaneously, right? So now you have a film of liquid water that is formed as the blade passes through the ice, and that kind of lubricates the interface of the ice and the blade, and that makes you advance faster. Okay, once you have passed through the ice, the pressure goes back to atmospheric, and that means that the little liquid water that you have formed will freeze over again. Okay, so those are a couple of examples in which we can actually see this anomaly of water, the idea that the freezing point gets depressed with increasing temperature. In the next video, we're going to explain what happens to the boiling point, why does it increase with pressure, and then we'll explain applications of that. And then we'll actually change this explanation to see what happens to the freezing point, to the boiling point, and the freezing point when you decrease the pressure as opposed to increase it.